tutor, Michael Kreter, is actually an expert in analyzing data from this Fermi Gamma Ray Space Telescope. All the data that they produce are immediately public, so anybody can go in, look at those data, analyze them quite diligently. Now, to even higher energies, so this works for photon energies maybe from a few hundred mega-electron volt up to maybe a few tens or even 100 giga-electron volt. But there's photons, there's gamma rays with even higher energies, and that's where a new technique comes in. These photons are of course still absorbed in the atmosphere, they don't hit the ground, but they have so much energy that, just like in Fermi, they make an electron-proton pair. These pairs have so much energy that they radiate more gamma rays. They still have enough energy to make more pairs. Again, more and more and more. So from this one gamma ray of the tera-electron volt, so TeV, remember optical light has eV electron volt, tera-electron volt is 10 to the 12, so that's 1 trillion times the energy of visible light. So this really probes regions of the universe where particles must have extreme energies. So 1 trillion times more energetic than what happens here on Earth, essentially. So these photons slam into the atmosphere and produce a whole shower of secondary particles. These particles all move extremely fast, actually faster than the speed of light in medium. The speed of light is c in vacuum. The medium speed of light is actually somewhat slower. And suddenly particles can move faster than the speed of light. And that produces something like this supersonic boom that you see from supersonic, here from supersonic aircraft. Essentially the trail of their light behind them all bunched up, and that's a light we call Cherenkov light. There's specialized Cherenkov telescopes, and then make very rapid succession images of these kinds of showers. And we have more than one telescope, we can actually nicely reconstruct exactly where that came from. The big problem with this is that there's not only photons, there's also particles, protons and electrons, cosmic rays that also slam into the atmosphere and do essentially the same thing. And there's actually only one photon on about 1,000 of these background protons. So the big problem, the big trick that had to be figured out is how to throw away those 1,000 protons that we're not interested in to find that one gamma ray that we actually want to see. So that actually took the community about 30 years to figure out how to do that before this could actually be used as an observational technique. And this is what HESS is for, a high energy stereoscopic system. And we are very much involved in that. In fact, Marcel will go there for observations in about 3 weeks, is it, right? And so all of the students in my group, in Christo's group, our high energy group, once or twice or even more get the chance to actually go to this observatory and do hands-on observations. There always have to be 2 scientists right there on site to supervise the observations. It's probably going to be 3 scientists again very soon. So this is located about 140 kilometers west-southwest of Windhoek in Namibia, and it is the world's largest gamma ray observatory. There's 2 other very big leading facilities. One is Veritas in Arizona in the US, one's on the Canary Islands off the coast of Northern Africa, it's MAGIC. But this central telescope here, this 28-meter telescope, that really is the world's largest Cherenkov telescope. And even the next generation telescope, Cherenkov telescope array that is hopefully starting to be constructed next year will not have a telescope as large as this one. So this will stay the world's largest Cherenkov telescope for a long time to come. That's 13 countries that operate this. Of course, Namibia and South Africa are very much involved. We have the largest group in HESS outside of Europe. WITS and FreeStack also are involved. Marcel is going, Christian is actually also going on HESS shift in September, I think. Good, so what do we see? This is a map showing the whole sky. The projection here is that this is the plane of our Milky Way and north-south pole of the galaxy. See that there's a lot of sources of these extremely high energy gamma rays in our own Milky Way, mostly pulsar wind, nebulae, supernova remnants, and a number of sources outside that actually do not belong to our own Milky Way. Go through this. This is essentially the same for Fermi gamma ray space telescopes, so some lower energies. So what kind of sources we see in gamma rays is, well, first of all, we see this right below here of essentially gas in the Milky Way. I've mentioned these cosmic rays, high energy particles that penetrate all of space. They can slam into this gas and thereby actually produce gamma rays. So that's how we essentially trace gas and gamma rays. But then there's individual point sources like pulsars. So Christoph Venter is a fan of these things, these collapsed remnants of very massive stars that explode in a supernova. The core collapses down into an extremely compact object. It's called a neutron star. It has about the mass of the entire sun, but collapsed down to a ball of about 10 kilometers. So it's extremely dense. It's got the density of material in an atomic nucleus. That's the analogy. If you had a teaspoonful of neutron star material, it would be about 2 billion tons, not including the weight of the teaspoon. So those are the things that Prof. Venter is studying and his group. Then there's these supernova remnants. So the core collapses, makes a neutron star. The rest shoots out, produces huge shock waves that make radiation throughout the electromagnetic spectrum. Yuri Sush, who's coming next year, is studying in particular particle acceleration that makes the gamma rays in the supernova remnants. And there's binary systems, so systems where we have a black hole, a neutron star, and a normal star right next to it. The black hole and neutron star sucks in material from this companion star. And in some cases, mostly this produces X-rays, but there are about 6 of these sources that also shine bright in gamma rays. So these are called gamma ray binaries then. That's something that I've also been working on quite a bit, including as well. And then outside, so these are all within our own galaxy. One of these things actually we also see in the Large Magellanic Cloud, and also supernova remnant we know in the Large Magellanic Cloud that makes gamma rays. All others of these pulsars and binary systems and neutron stars, they are all supernova remnants. They are all belonging to our own galaxy. But then there are sources outside of our galaxies, and those are active galaxies. Those are other galaxies, millions of light years away, billions of light years. Those are quasars, for example, and other kinds of AGN, and I'll talk much more about AGN now. So some, I'll discuss this more, and then there's a class of active galaxies called radio galaxies. Okay, let's spend a few minutes more on these AGN, so active galaxies. We pretty much know that all galaxies, just like our own Milky Way, have a very massive black hole in the center. Anybody know what's the black hole in our own Milky Way, how much mass that has? It's about 4 million solar masses. So 4 million times the mass of the sun is collapsed there into one huge black hole in the center of our Milky Way, and all galaxies are like that, as far as we know. But there are a few galaxies where these black holes then have so much mass to suck in that gas heats up, and in addition to heating up, it's not only sucking in gas, it's also spewing out gas at the same time. It's probably a way for the system to lose angular momentum, that some of the materials just fly out probably along one of the magnetic field lines. So in our own Milky Way, the black hole essentially has nothing to feed on. It's very empty near the central region of our Milky Way. That's why our own galactic center is a very faint X-ray source, and we don't even really see it in gamma rays very much. But if there is a lot of gas to suck in, then these black holes become active, and in about 10% of the cases, we see bright jets or streams of gas shooting out. So this is what they look like. So the actual center of the black hole is sitting right here. And we see that there are these streams of gas shooting out hundreds, thousands, 10,000s of light years into space. And it's actually quite a miracle, not really understood why they remain so perfectly collimated. Plasma physicists know so many instabilities in plasma, people think they might disrupt immediately. If you imagine, it's a very small region of maybe the size of our solar system that accelerates a jet and then stays straight over millions and trillions of times the size of the region that it actually accelerated. So how that works, that is really one of the big mysteries of how nature manages to do that. So you see that within these jets, they're not just perfectly smooth and homogeneous, they're individual blobs here. And exciting about those is that one can do very high resolution radio images of these and follow these blobs over long times. You see time here from 1997 that started, 1999, 2000. And you see the black hole sits somewhere here, and the jet shoots out. This is the very inner region of the jets. The structure is, of course, much larger here. This is very high resolution, zoomed into the very center. You can follow how individual blobs are moving. Now, if we know how far away this is, we see it moving across the sky, we can convert that into the speed, right? And if you calculate what the speed is with which that's moving, you get the impression that's 10, 20, 30 times the speed of light. Now, does that mean that everything with discussed with relativity is bogus now? Hopefully not. So this is a phenomenon called superluminal motion, and we seem to see things moving across the sky with many times the speed of light. So that's a phenomenon that is very similar to what we've seen in our relativity movie when the policeman saw the car coming at extremely high speed, because the light that the car was emitting was essentially just a little bit before the car, and all the light waves essentially bunched up, reached the police car in a very short time, much shorter time than they were emitted. We see the exact same thing in action in these active galaxies. There's a jet that we pointed close to us, so we are sitting somewhere right here. The jet emits light at a time as it moves along the jet here, and it only stays right behind the lights that it has just emitted. So by the time it reaches us here, we see it in very short succession, and that gives us the impression that it moves up way faster than it actually is, because we see the time compressed due to this light travel time effect. So exactly the effect that we saw illustrated in the movie, we see in real life action in these images here, where these blobs seem to be moving faster than the speed of light. So what happens then? So now we know we have a situation where something moves almost right at us with essentially the speed of light, almost the speed of light. So again, if you do the high energy astrophysics class for master, you'll learn that so if you have 40 times speed of light, that means the Lorentz factor with which the stuff is moving has to be at least 40. So the amount of superluminal speed gives you a direct lower limit on the actual speed of the motion. Because the Lorentz factor of 40 still means you're not quite speed of light, but almost speed of light. So we have now something like the blobs moving along the jet, radiating in all directions at some frequency called the prime. Things they are varying on some kind of time scales. Then what happens? When this moves with a high Lorentz factor, say towards us, we're sitting here, then that's of course why I spend so much time deriving this Doppler boost, this Doppler factor here. So 1 over gamma 1 minus beta cosine of the observing angle. Then we have relativistic aberration. Everything is bunched up in the forward direction. And that means we have the intensity, actually, the flux per area increased by 3 of these Lorentz factors, these Doppler factors. So now if we typically have a Doppler factor, a Lorentz factor, maybe 10 or so, Doppler factor 10, that means the flux of radiation appears actually 1,000 times brighter than what it's actually producing, just because of these weird relativistic effects. The frequencies that enhance Doppler boosted, so red blue shifted, and those frequencies are the inverse of time intervals. So if the source itself is actually varying, say, on a scale of a day or so, then we see this very much shorter on time scales of tens of days of hours. And in fact, there are some of these sources that we see in gamma rays, we actually see this varying on scales of just a few minutes or so. Considering that the gamma ray sources here, the central sources, are actually hundreds of thousands of times brighter than the entire galaxy, hundreds of billions of stars. These tiny little regions here are the size of our solar system, is hundreds of thousands times brighter than that entire mass of 100 billion stars. And yet, it can be varying in time on scales of just hours or even just minutes. So that is extreme conditions, some of the things that we are studying. And so in fact, the sources where these jets are now pointing almost at us, you're probably wondering here, these jets, does this mean you see the jet only on one side? Does that mean that there is only one jet? Is that what you would expect? That's most likely not, because you see already this dissipation, this hot spot on the other side, right? So what happened to the jet here? Yeah?
I'll venture a guess and say it's Doppler shifted.
Exactly, right? This is the jet that points towards us. Everything is headlight shining at us, right? It's the same jet going that way, but that's pointing that way. Right? It's all being in that direction. So it's too faint. Whatever's left going this way is just too faint to see. So this tells us that really we're dealing with a jet that is pointing very close to our line of sight. The radiation we see from here is Doppler boosted. We see it much brighter. It's these kind of AGN that we call blazars. So if we have these active galaxies where the jet points almost right at us, and most of the sources outside of our Milky Way that we see with Hess and with Fermi are actually these kind of blazars. And those are in fact the main aspect that I am studying in my research. So if this is something, gamma ray astronomy in general, maybe especially AGN, there's many other aspects of gamma ray astronomy that I study, but this is kind of a focus area. You're looking for a master's project if you think this is something that might be exciting or fascinating. I've posted 2 projects, but we don't have to restrict it to that. If you don't like those, we can always come up with others. So if this is something that you think you might find fascinating, please feel free to just stop by and talk when you're looking for a master's project. That's all I had. Waiting time for a break. Anything else you'd like to know and discuss? Any questions?
These jets, the way I understand it, like you talked about it now, it's the gas around the black hole or whatever that's being accelerated and something to do with angular momentum that makes it. These gas it's not emitted from within the region of the what do you call it, the event horizon. It's not coming out of the event horizon.
Right, nothing comes out of the event horizon. All of this happens right outside the event horizon. Again, it's not quite clear what really powers these jets. It can either be that you have if there's an accretion disk, there's magnetic fields are everywhere. If now the gas swirls around rapidly, has magnetic fields built in, and these get wound up and naturally kind of provide a funnel where gas can stream out. If gas gets flung out a little bit, it's naturally, essentially flung out these magnetic fields. But this has to happen before material actually gets swallowed into the event horizon.
Okay.
Once that has happened, nothing comes back out.
Yeah.
It's also an idea that actually if magnetic fields thread through the black hole, then actually one can extract rotational, black hole rotates, then one can actually extract energy from this rotation and shoot jets out. But still, whatever goes out has to be outside the event horizon.
Okay.
So exactly what powers these jets, how they are launched, that is one of the things that we're trying to address with our research. There's still so much not understood in the physics of these jets. Any other questions? If not, then thank you all for your patience. That's the final exam on the 14th. Will of course be not more difficult than the midterm exams. You know about what to expect. The only thing is, of course, that it's cumulative over the entire semester. So it can have everything from potentials to relativistic electrodynamics. And thank you all. See you all soon. Some other occasion.